Okay, so today we're going to be talking about gas behavior. So we're talking specifically about, excuse me, different relationships of different properties of gases. So we've talked about volume and pressure and different characteristics that apply to all states of matter, but gases behave a little bit differently than solids and liquids do. So that's why we're going to go over this state specifically with a few special properties. So first off, temperature. Everything has temperature. Um, the definition of temperature itself is the measure of how fast the particles in an object are moving. So the faster the particles are moving, the higher the temperature is. That's a misconception. There's a misconception a lot of times that it is that people think that the higher the temperature, the faster the particles, but it's actually related the opposite way. The particles moving faster is what makes the temperature go up, not the other way around. So when those particles get a lot of energy, they have a lot of kinetic energy to move around. That's what creates that causes that temperature to go up because it's the measure of how fast they're actually moving itself. Um, Temperature when it rises, makes gases expand. So if you have ever left a basketball outside or some kind of ball that you have to inflate, left that outside over the winter, you may notice that it deflates. It's going to deflate, maybe not all the way, but depending on how cold it gets, the colder it gets, the more it deflates. If you continue to leave it outside, as it warms back up outside, it's going to refill. It may not refill 100%, but for the most part, it refills back to what it was originally. So the gas inside of that ball, all it's doing is it's contracting. It's when it gets cold out, and then once it gets warm out, it's going to expand back out that way. So we'll talk about a law that has to do with that, and we're gonna be doing some lab demos with that too. All right, a characteristic again of all states of matter, but one it's slightly unique for gas is volume. Again, the amount of space that an object takes up is the definition of volume. So with gas, remember this was our one state of matter that had an indefinite volume. So it just depends on what container that gas is in. So if you have gas inside of a jar, it's going to obviously have a smaller volume, but you open that jar up, you let it out, and it's going to have a bigger volume. So it's going to expand to wherever it's at. So gas particles can freely move and can freely expand, which is why volume is a unique characteristic for them. Okay, so the third factor that we are looking at when it comes to that is somewhat unique to gases is pressure. So pressure is the amount of force exerted on a given area of surface. So air has pressure. Everything has pressure, but air has pressure, and that is the force that all the air particles are exerting on everything around it. We also look at pressure as the number of times that the particles of a gas hit the inside of their container. So whether the inside of their container is a jar, it's a room, it doesn't matter. It's just how many times it's hitting the inside of that container. The higher the hits, the number of hits, the higher the pressure is. So one thing about pressure is that if we have more particles, there's going to be higher pressure. Because if you add more particles into a space, now you have more chance of those particles hitting the inside of that container, and that's going to create a higher pressure. So this is the third, also with volume and temperature, third of our factors that we are looking at, and we're going to look at gas behavior laws and see how they're related and how they react to each other. So what happens to temperature as volume does this, and so on and so forth. So our first gas behavior law is called Boyle's law. So the definition of Boyle's law is for a fixed amount of gas at a constant temperature, the volume of the gas is inversely related to pressure. So to break down this definition, it says a fixed amount of gas. So we have a number of particles are not changing. It's also at a constant temperature, so temperature is not changing at all. The volume of the gas is inversely related to the pressure. So inversely means that it's doing opposite of each other. So as one goes up, the other goes down. So if you have a gas and you increase the pressure on that gas, it's going to cause the volume to decrease because you're putting pressure, you're pushing that in, and you're making that volume contract. And the opposite is also true. If you were to decrease the pressure, then that volume, that those particles are allowed to expand, and that makes it so the volume is going to increase. Same if you look at, if you are changing the volume. If you increase the volume of a container that the gas is in, now you're decreasing the pressure because there's more room for those particles to move around. So now there's less collisions against the inside of that container that are going to happen. If you decrease the size of that container and the volume of that container, it means that it's going to have a higher pressure because now there's less space for them to move around and there's more of a likelihood of the particles hitting the sides of the container. So if you look at that equation there, the I's after the P and the V there stand for initial, and the F's after the P and V stand for final. So we are saying that the initial pressure, which is the starting pressure, times the initial volume equals the final pressure times the final volume. So if you know all three of, or if you know three of those four variables, you can easily solve for the one that's left. So if you know what the gas started at for pressure and volume, and you know what it ended at for pressure, you can find out what it ended, or what it wound up being volume-wise. So just to give you a little example here, we're not going to do a ton of math when it comes to these. We're not going to focus too much on the math. I just want you to know the concept mainly. Try your best not to make fun of my drawing again, because it's going to be absolutely horrible, my writing. So let's say our initial pressure, that's an arrow, is 2. So that's supposed to be a 2. Our initial volume, so we have initial pressure, that's supposed to be a dot for multiplying, times, let's say our volume is 3. And that equals, let's say we don't know the volume, but we do know the pressure. So we know that our final pressure is 6, but we do not know, again, that's supposed to be a multiply sign, we still do not know the volume. So I'm going to write VF for final volume. So we want to know what the volume of our gas is after there's been a change. So you just solve this out. So 2 times 3 gives us 6. This is better than last time, but still not good. Equals 6x essentially. I'm just going to write an x to simplify it because we just need a variable there. And then that comes out to be x equals 1. So that means that when the pressure is 2, that the volume of that gas in this situation will be 3. But when you change the pressure to 6, then the volume is going to go down to 1 because they are inversely related. So that's just an example to show you how to use that equation. All right, and our last law is Charles's law. So this says for a fixed amount of gas at a constant pressure, the volume of the gas changes in the same way that the temperature of the gas changes. So again, let's break this down. First off, the fixed amount of gas. We still have the same amount of particles no matter what. It states at a constant pressure. So this time the pressure isn't changing throughout. And it's saying that the volume of the gas is changing in the same way that the temperature does. So as one goes up, the other also goes up. So if you have, let's say, an increase in temperature, we know that gas expands as you increase in temperature. So if you have a basketball and the temperature increases around that basketball, the gas inside that basketball is going to expand. So the volume is going to go up. So as temperature goes up, the volume goes up. Same for the opposite. If it gets into the cold, the temperature goes down, it makes the volume go down. So they are directly related. So as one's going to increase, you know the other will increase. So again, let's just look at this equation here. This time we have some dividing that shows the direct relationship they have. So we take initial volume divided by initial temperature, and that equals final volume divided by final temperature. So again, just a quick, we can do a quick little practice here. Let's say we know that our final volume, or excuse me, let's say, okay, we want to know what our starting volume is. This is what we are looking for. We didn't know how much volume we started with, but we knew how much we ended with, and we knew the temperature to start and to end. So let's say We don't know starting volume. We know our starting temperature was 10. Again, excuse my writing. Starting temperature was 10. And we also know that we ended with a final volume of 20. And we ended with a final temperature of 2. So if we solve this out, you can cross multiply however you choose to do this, but if you cross multiply, you get 2x equals 200. If I could actually write with this mouse pad. So then that comes out to being x equals 100. So that would mean you would know that the start of your starting volume was 100. So when, for this particular gas, when the volume is 100, the temperature will be 10. And then the volume decreased to 20, so it decreased to 2. So it decreases by the same proportion, so that each went down to 10% of the original number. So again, we're not going to focus a ton on those on the math part, but I did want to just sit and show you that so you can kind of get the concept that we're going to be looking at when we do this in the lab.